Welcome to the deep dive, where we take complex technical documents and really pull out the essential knowledge, giving you a deep understanding without all the noise.
And today, we are tackling what is, I think you could argue, the single most foundational challenge in all of modern computer
We're
science,
talking about concurrent programming.
specifically the problem of mutual exclusion.
Right. I mean, this is the bedrock issue that every multi-core processor, every operating system, every high-performance app has to solve. How do you get dozens or, even thousands of these independent workers, these threads, to share data without stepping on each other's toes?
Without corrupting it or crashing the entire system.
Yep.
It really is the essential coordination problem.
So it's all about not messing things up when everyone's trying to talk at once.
That's right. And our source material today is drawn from some really foundational texts on concurrent data structures and multiprocessor programming.
And our mission for this deep dive.
Our mission is to really understand the language of concurrency, define the properties we need for safety and for liveness, and then look at three truly classical software solutions.
And then we'll wrap up by looking at the theoretical limits, the things that ultimately pushed us toward hardware-based fixes.
Exactly.
Okay, so let's ground this right away with a tangible example. The sources bring up this classic scenario of threads trying to find prime numbers.
Yeah, this is a great example. So imagine you have, say, 10 threads, and they're all churning through a massive range of integers to see which ones are prime.
You wouldn't want to just give each thread a static block of numbers, like you take the first million, you take the second million.
No, that's really inefficient. What if one thread gets a block with lots of easy-to-check numbers and finishes early? It just sits there, idle.
Right.
A much better approach is a dynamic work assignment. You use a single shared counter object.
Okay, so this counter just keeps track of the next number that needs to be checked. A thread finishes its work, comes back, and says, what's next?
Precisely. It requests the next number available. And to do that, it needs to execute an operation we call get an increment.
Get an increment. Sounds simple enough.
It seems simple. The thread reads the current counter value. Let's say it's 100. It then increments the value that's stored in memory to 1011 and returns the original value, 100, back to the thread so it can start its work.
But the key realization, and this is everything, is that this whole operation, the read, the modify, and the write back, it all has to be atomic.
Yes. Indivisible.
Yeah.
It has to appear to happen all at once, instantaneously.
Because if it's not atomic, you get the nightmare scenario.
Let's walk through it.
Yeah.
Imagine two threads, we'll call them thread A and thread B,
Mm.
and they hit that counter at almost exactly the same time. The current value is 100.
Okay.
Thread A reads the value. It sees 100.
Then thread B, just a microsecond later, also reads the value. It also sees 100.
Right. Now, thread A increments its internal copy to 101 and writes 101 back to the shared counter.
And then thread B, which is completely unaware of what A just did, does the same thing. It increments its copy to 101 and writes 101 back.
So what's the final value in the counter?
It's a 101, but it should be 102.
It should be 102. We've had two increments, but the state only reflects one. We've completely skipped checking the number 101, which might have been a prime, and our shared state is now corrupt.
And mutual exclusion is the mechanism we use to prevent that, to make sure only one thread is in that critical part of the code at any one time.
And solving this isn't just about correctness. I mean, that's essential, but it's also the key to performance. And that brings us to Amdahl's law.
Ah, Gene Amdahl. He basically established that the speed up you get from parallelizing something is fundamentally limited by the part of the code that has to run sequentially.
Exactly. Let's really unpack that.
Okay, so if, say, 90% of my prime finding code is parallel, the actual heavy computation, but 10% of the time is spent waiting to hit that shared counter.
Then the performance ceiling that 10% sequential part imposes on you it's brutally low. It doesn't matter if you have 4 cores or 1,000.
You can only ever get a 10x speed up at best.
At best, that is your absolute theoretical maximum. But if we can optimize that sequential coordination, that little critical section, down to just 1% of the total time,
Then suddenly your theoretical maximum speed up jumps to 100 times.
that is a massive difference.
It's huge.
And that's what Amdahl's law tells us. It says our top priority in performance engineering has to be making those necessary sequential parts as tiny and as blindingly efficient as possible.
Which is why studying how to solve mutual exclusion is. It's the foundation for all high-performance computing.
It really is.
So we have our mission. We
Okay.
need to figure out how to build a lock that guarantees safety and progress and is also incredibly fast. We should probably start by laying the theoretical groundwork, right? The language of time and correctness.
Absolutely. We have to start there.
So if we're going to talk about whether two operations overlap, or if one happens before another, we need an agreed upon definition of time.
We do.
When you have things happening concurrently across different threads, maybe even different processors, what does when even mean?
You have to begin with an abstract shared reference point. And for this, we go all the way back to Isaac Newton.
Newtonian time.
Yep. We rely on the concept that time itself, what he called absolute true and mathematical time, just flows equably, independent of any observer. This common linear timeline is essential for us to reason about concurrent events.
Even if the threads themselves don't have, like, a perfectly synchronized clock.
Right, even then,
Yeah.
we just assume this absolute timeline exists.
Okay, so timeline established. Now let's build a vocabulary of concurrency on top of that.
The basic building block is the event. And an event is really simple. It's just a state transition within a thread.
So like a thread reads a variable, that's an event.
A thread writes a variable, that's an event. A thread is really just a state machine, moving from one event to the next.
Okay, and the duration between two events, say an operation's start and its end, that's what we call an interval.
Correct. And then if we look at two events from, say, two different threads, $80 and $1, and we could definitively say that $2 occurred strictly earlier than $1 on our absolute timeline.
Then we have a precedence relation. We can say $8 precedes $1.
And this precedence relation creates what we call a total order on events. We know exactly which one happened first. It gets a bit more complex with intervals, but the idea is the same. If the final event of interval A happens before the starting event of interval B, then A precedes B.
They're cleanly separated, no overlap.
Exactly.
But the really interesting part, the whole reason we're having this conversation, is when that doesn't happen, the definition of concurrent.
Right. So if you have two intervals, $8 and 1, and you absolutely cannot establish a strict precedence relationship,
Meaning A doesn't precede B and B doesn't precede A.
then those intervals are concurrent. They overlap on that shared timeline, maybe partially, maybe entirely. And reasoning about how those overlapping concurrent intervals interact, that is the entire challenge of this field.
So really, concurrency is defined by the lack of a clear before and after relationship.
That's a great way to put it. It's ambiguity.
Huh.
And our job is to manage that ambiguity.
Okay, so we have this abstract time framework. Let's apply it now to the real problem of protecting data. Where does this concurrent danger actually show up in our code?
It shows up in what we call the critical section, or CS for short. This is a very specific, usually pretty small segment of code where a thread is accessing or modifying shared data.
And what's the mechanism that defines that section?
Well, to enforce protection, every critical section has to be guarded. It's bracketed by a lock call at the beginning and an unlock call at the end.
So in our prime number example, the get and increment operation, the read, the modify, the write back, all of that would be wrapped inside this lock-unlock structure.
It has to be.
The lock is the digital bouncer, only letting one thread into the VIP section, the CS at a time. Let's just hammer this home one more time. Why is mutual exclusion absolutely mandatory?
Because if multiple threads enter that critical section concurrently, the results of the computation just can't be guaranteed as correct. We saw it with the counter example.
Right, two increments result in the state only changing by one.
And that's a classic data race.
Yeah.
If you let threads just freely interleave their access to shared memory, the final state depends entirely on the unpredictable timing of those operations. It's non-deterministic. Mutual exclusion gets rid of that ambiguity by forcing them to access the resource one by one, sequentially.
Okay, so once we agree we need mutual exclusion, we need a checklist. What makes a good lock algorithm? And here we get into the two main categories, safety and liveness.
This distinction is so critical. Safety properties are about making sure that nothing bad ever happens.
And liveness properties are about making sure that something good eventually happens.
And a correct functional system needs both. You can't have one without the other.
Let's start with safety, the absolute prerequisite.
Which is mutual exclusion itself. ME is the cornerstone safety property.
Yeah.
And defined precisely, it means that the critical sections of different threads must not overlap in time.
So if we look at the intervals for thread A's critical section and thread B's critical section,
one must entirely precede the other. Either CSMAT happens before CSP or CSP that happens before CSP. There is absolutely no concurrent overlap allowed.
if you violate that, you've compromised your data, your system has failed its correctness test. End of story.
End of story.
Okay, that covers integrity. Now for progress. We need liveness to make sure the system doesn't just grind to a halt waiting for a lock that never opens.
Right. And the most basic progress guarantee here is freedom from deadlock.
Deadlock.
It states that if one or more threads are trying to acquire the lock, then some thread will eventually succeed.
That's a really key distinction there.
Yeah.
Some thread. It doesn't say which thread.
No, it just means the system as a whole never freezes entirely. It keeps making overall progress.
Even if one individual thread might be stuck waiting forever.
Exactly. Deadlock means the whole system is frozen, waiting for a condition that will never be met. Deadlock freedom guarantees the system won't get into that kind of irreversible stall. But like you said, it's a relatively weak guarantee for the individual.
Which is why we aim for the stronger measure, freedom from starvation, sometimes called lockout freedom.
Right.
So what's the difference? What separates this from just being deadlock-free?
Starvation freedom raises the promise from the system level to the individual thread level. It guarantees that every thread that tries to acquire the lock will eventually succeed. Every single call to lock must eventually return.
So this prevents the scenario where thread A is waiting patiently, but a continuous stream of threads B, C, and D keep jumping the queue, entering and exiting, while A just waits forever.
Correct. Starvation is a failure of fairness. A starvation-free algorithm is, by definition, also deadlock-free, which makes it the gold standard for liveness.
So when we look at these classical algorithms, we're checking them against this trifecta: mutual exclusion for safety, and ideally starvation freedom for strong liveness.
That's the bar.
Okay, so before we get to Peterson's famous lock, it's really helpful to look at the attempts that came first and failed.
Oh, absolutely. These initial failures are crucial because they show you just how subtle this problem is. It's incredibly hard to solve both safety and liveness at the same time.
So let's start with the most intuitive first try. We can call it lock-on.
Lock-on is what you might call the polite mechanism. A thread signals its interest by raising its flag. So flag A true.
Hey, I'd like to come in.
Exactly. Then it checks if the other thread is interested, so it looks at flag A. If the other thread's flag is down, it proceeds into the critical section. If the other thread's flag is up, it waits.
And this is great for safety, right? It guarantees mutual exclusion.
It does. I mean, for both threads to be in the critical section, A must have seen B's flag as false, and B must have seen A's flag as false. That's a logical contradiction.
Yep.
So ME holds.
But it fails spectacularly on liveness.
Spectacularly. Imagine this interleaving. 1. Thread A sets its flag to true.
2. Before A can check, thread B sets its flag to true.
3. Thread A now checks B's flag. It sees it's true, so A waits.
And 4. Thread B checks A's flag. It also sees it's true, so B waits.
And they're stuck forever, each waiting for the other to lower its flag, which will never happen. That is a classic deadlock. Safety guaranteed, liveness failed.
So the next try, Lock 2, tried to solve that deadlock by introducing a sense of deference.
Right. Lock 2 introduces a shared variable. We'll call it victim. When a thread wants to enter, it first says, I'll let the other thread go first by setting victim to its own ID.
I'll be victim.
I'll be the victim. Then it waits only if it is still the designated victim.
This sounds like it fixes the deadlock. If they both try at once, only one of them can be the last one to write to the victim variable. So the other one will see that it's not the victim and can proceed.
Correct. It is deadlock-free. But it fails a safety test. It fails mutual exclusion under certain race conditions.
How?
Well, imagine thread A is running really fast and thread B is delayed for some reason.
Okay.
1, thread A sets victim A2. 2, before A can check, thread B runs and sets victim A of B. So B is now the victim.
3, thread A now checks the wait condition. It sees the victim as B, so it's not the victim. A enters the critical section.
So far, so good. ME holds for a moment. But the failure happens if one thread is arbitrarily fast or slow after that victim variable has been set. The sources show they're basically complementary failures. Lock 1 is safe, but deadlocks. Lock 2 avoids the deadlock, but isn't safe if the thread speeds are asynchronous. It just highlights how hard it is to combine a safety mechanism like the flags with a liveness mechanism like the victim variable.
Which brings us to the genius of Gary Peterson's 1981 algorithm. He realized you don't have to choose. You can use both variables, but you have to combine them in a very specific way.
Exactly. This is the first fully correct two-thread solution using only reads and writes. And the key, as you said, is how it combines the flag array and the victim variable. The flag signals interest, and the victim acts as the tiebreaker.
Okay, so a thread wants the lock. What's the sequence?
First, it states its interest. It sets its entry in the flag array to true. flag A true.
Then second, it yields the right-of-way. It sets itself as the victim, victim A.
And here's the crucial synthesis, the wait condition. A thread only waits if two things are true at the same time. The other thread is still interested, flag B is true. And D, the thread itself, is the declared victim. Victim is A.
Let's really focus on why this guarantees mutual exclusion. We can frame it like a logical puzzle, which is basically how the proof works, by contradiction.
Let's do it. Assume the impossible, that two threads, A and B, are somehow concurrently inside the critical section.
Okay, so if A is in the CS, it must have gotten past its wait loop.
Right. Which means after it set flag A equal true and victim A, it must have observed a state where either B was not interested, flag B was false, or our B was the last one to be named victim. Victim was B.
And same for B. If B is in the CS, it must have set its flag and set the victim to B, and then it must have seen a state where either flag A was false or victim was A.
Now, since both are in the CS, we know they both must have set their flags to true. So we can rule out the flag A equals false condition.
Right, that can't be it. So they must have both entered based on the state of the victim variable.
Okay, focus purely on that victim variable. Both A and B wrote to it. One of those writes had to be the final one before they both checked the condition. Let's just assume B's right, victim B happened last.
So on the timeline, A wrote victim A and then B wrote victim EB.
Okay, so for A to get into the CS, it must have checked its wait condition after B wrote victim equals B. A would see that victim is B, so its wait condition, flag B is true, A and D victim is A, would be false. A gets in.
That seems plausible. A gets in. Now what about B?
Well, for B to get in, it must have checked its wait condition.
Yeah.
What was the state of victim when B wrote to it? It must have been A, because A wrote first.
Right.
So B's wait condition is flag A true. Yes, it is. And is victim equal to B. When B checks, it sees that victim is still A because it hasn't written its own value yet. Wait, no, the logic is even simpler.
Let's back up. B's right. Victim BB is the last right.
Yes.
What?
So A's right, victim EA happened before it.
Okay.
So A gets to its wait condition check.
Yeah.
If it reads victim before B writes, it sees victim as A and it waits. If it reads victim after B writes, it sees victim as B and it enters. Let's assume the latter A is in the CS.
Okay, A is in, Joff B. B just wrote victim equals B. Now it gets to its wait condition.
B checks. Is flag A true? Yes, A said it. Is victim equal to B? Yes, B just said it.
So the wait condition is true. B has to wait.
B has to wait. The contradiction is established. The thread whose right to victim happened last is, by definition, forced to wait if the other thread is also interested. It's impossible for both to get through.
That is just beautiful. It's so elegant. That simple act of setting the victim variable and then checking provides a definitive sequential reference point.
It guarantees one thread yields if there's contention. And because one thread is always guaranteed to proceed, it's also starvation-free. An elegant, complete solution for two threads.
For two threads. But in a world with 64 cores, we're going to need more. How do you generalize this?
That's where the filter lock comes in. The source material describes it as an n-thread generalization of Peterson's logic. You can think of it like a funnel or a hierarchy of competitions.
A funnel suggests layers, right?
Exactly. The filter lock uses 101 levels from level 0 up to another 1. To get to the final critical section, a thread has to successfully pass through every single level. It's a gauntlet.
Okay, so walk me through one level. What happens?
To enter, say, level $+ plus $2 a thread first has to declare its presence at level $1. At each level, there's a competition similar to Peterson's, where threads might have to wait for other threads at the same or a higher level.
So it's like a series of N1 Peterson locks, one after another.
That's a good way to think about it. At level $J, a thread is competing with, at most, $0 other threads. The logic ensures that at least one thread is always guaranteed to pass from level $J up to level J plus all 1.
So if 5 threads are all fighting for the lock, they climb from level 1 to level 4. At each level, some might get held back, but at least one makes it through, until at level 4, only one winner remains.
Precisely. And because of this structure, the filter lock successfully guarantees mutual exclusion for n threads, and it also ensures deadlock freedom. The system as a whole will always make progress.
Okay. You said at least one makes progress. That sounds like it has a major drawback.
It does. It fails to guarantee starvation freedom. Because the mechanism only guarantees that some thread makes progress at each level. A thread that's consistently slow or just unlucky can be perpetually forced to wait for faster threads. Faster threads can essentially leapfrog or overtake slower ones between the levels. A waiting thread could, in theory, be locked out forever.
So it's deadlock-free, but potentially unfair, which means we need an algorithm designed specifically for fairness.
And that brings us to Leslie Lamport's seminal contribution, the bakery algorithm. This solves the end-thread problem while guaranteeing first-come, first-served progress, FCFS.
Ah, the famous bakery analogy. The deli counter. You take a number at the door.
It's one of the most intuitive analogies in all of computer science. And that doorway is the first section of code a thread runs when it wants the lock.
So what happens in the doorway?
A thread does two crucial things. It raises a flag to show it's interested, and then most importantly, it generates a unique ticket or label.
And how does it get that label?
It reads the labels of all other competing threads. Then it sets its new label to be one greater than the maximum label it saw.
Okay, but what if two threads hit the doorway at the same time? They could both read the same max label, say 5, and they both pick 6 for their new label. Now you have a tie.
Right, and this is where the mathematical elegance comes in. Lamport breaks ties using a precise lexicographical ordering. You don't just look at the label, you look at the pair. Blah, blah, blah.
The ticket number is the first part of the comparison, and the thread's unique ID, I, is the second part, the tiebreaker.
Exactly. So if thread 1 has the ticket 6-1 and thread 2 has the ticket 6-2, thread 1 is always considered smaller. The lower thread ID wins the tie. This gives you a total unbreakable order.
And once a thread has its ticket, it waits. It checks all the other threads.
And it only proceeds into the critical section if there's no other thread with a raised flag that has a lexicographically smaller ticket.
Let's talk about that fairness guarantee. Why is this specifically first come, first served?
The guarantee is all in the doorway operation. If thread A's doorway execution happens completely before thread B's doorway execution.
So on our absolute timeline, DAD precedes DA.
Right. Then A must have finished writing its label before B even started calculating its own.
So when B read all the other labels, it must have seen A's label, and it would have picked a number that was strictly greater.
Exactly. Label rebels will be strictly less than label builders. So B is forced to wait for A. The first one to get a ticket is the first one to be served.
And because of that strict FCFS ordering, every thread that takes ticket is guaranteed to eventually be at the front of the line.
Which means the bakery algorithm isn't just correct for mutual exclusion and deadlock-free, it's also starvation-free. It was a perfect software-only solution to the end thread problem.
Okay, so we've established that this is solvable. You can solve mutual exclusion with just pure software constructs, reads, and writes. That's a huge theoretical win.
It is.
But as we start to move from theory to the real world, we run into the inherent costs and limitations of these beautiful, elegant solutions.
Right. We have to ask, how fundamentally expensive are they? And we can look at two main constraints: how much memory they need and the unbounded nature of some of the variables they use.
Okay, let's start with memory. If the only tools we give ourselves are basic reads and writes, how much memory is absolutely required to solve the deadlock-free mutual exclusion problem for, say, end threads?
This is a deep theoretical question, and it's answered by a theorem in the source material. It establishes that any deadlock-free lock for end threads, using only reads and writes, has to use at least omega n distinct memory locations.
Omega n. So in plain English, the memory you need scales linearly with the number of threads you have.
It'd have to.
But why? Why can't we just get clever and use, I don't know, a handful of global variables no matter how many threads are competing?
The proof is based on a concept called a covering state, and it's a contradiction argument.
Yeah.
We can maybe frame it less like a formal proof and more like a practical impossibility.
Let's try that.
Okay, imagine we have n3 threads, A, B, and C. But we only allow ourselves LPO2 shared memory locations to coordinate. Just two mailboxes, $M and $10 too.
These two mailboxes are the only way the threads can signal their intentions to each other.
Exactly. Now think about a state where A, B, and C are all trying to get the lock, but nobody has it yet. The system state has to be safe, no one's in the CS, and it has to be live. Someone has to be able to make progress. This is our covering state.
But with 3 threads and only 2 mailboxes, at least 2 of the threads must be trying to signal their intent using the same location, right? Or their combined intent looks identical from the memory's point of view.
That's the crux of it. Because you have fewer memory locations than threads, the memory state can't uniquely represent the state of every single thread.
So the memory could look exactly the same, whether it's, say, just thread A trying to get in, or if it's both A and B trying to get in.
Precisely. And if the memory state looks identical in those two scenarios, how can the algorithm proceed safely and without deadlock? If the algorithm is deadlock-free, it must allow some thread to make progress from that state.
Okay.
But if it allows, say, thread A to proceed, what about thread B? The algorithm can't even tell that thread B is waiting. B could be starved forever because the limited memory can't distinguish between the state A has been waiting a long time and A just showed up. The memory state just isn't rich enough to encode the full history and intent of all the threads.
It can't uniquely cover every thread's attempt without potentially breaking the deadlock-free promise.
Exactly. You need enough unique memory locations, one for each thread, basically, to guarantee that progress can always be made. And that forces the memory requirement up to omega n.
So the upshot is that Peterson's lock and the bakery algorithm, which both use memory that scales with n, are actually, in a sense, theoretically optimal.
In terms of memory requirements, yes, within a constant factor. But this is also what makes them costly for systems with thousands of threads.
Okay, now for the second limitation, the bakery algorithm. It's beautiful, it's fair, but it has a huge practical flaw.
A very significant one is the problem of unbounded growth.
The tickets, the labels, we know they are strictly increasing because that's what guarantees the first-come, first-served order. You always pick a label one higher than the max you see.
Correct. So if a thread enters and exits the critical section a billion times, its label is going to grow towards a billion.
And if the system runs long enough.
Those labels will grow infinitely large.
And in a real computer with, say, 64-bit integers, those labels will eventually overflow. They'll wrap around back to zero.
And the moment that happens, the entire ordering property collapses.
Yeah.
The fairness guarantee is gone. If a thread with a huge label like 2 to 4 all exits, and a new thread comes in and picks label 1, the system suddenly thinks the new thread has precedence over everyone else who's been waiting with large labels.
So the algorithm is mathematically perfect, but physically impossible to run forever.
Precisely. And this constraint is what led to a whole field of research into what are called bounded timestamp systems, which try to solve this problem of recycling the ticket numbers without breaking the ordering.
Okay, so this is the crucial pivot. We have these mathematically proven, even starvation-free software solutions. Why doesn't every modern developer just use the bakery algorithm? Why do they reach for a library function that uses hardware primitives?
It comes down to a really profound disconnect between the theoretical world where these algorithms were proven and the hard reality of modern chip architectures.
And what's that disconnect?
The proofs for Peterson and bakery rely on a very specific and very strong assumption about how memory works. It's called sequential consistency.
Right. Remind us what that means in practice.
Sequential consistency guarantees that the outcome of any execution is the same as if all the operations from all the threads were executed in some single sequential order. And critically, the operations of each individual thread appear in that sequence in the order you wrote them in the program.
If you write X1 and then you write Y2, the system guarantees that everyone everywhere sees X1 happen before Y2.
Yes. But modern CPUs, they don't work that way.
Right.
They're built for speed above all else.
And they use tricks that violate that consistency model.
Absolutely. To maximize performance, they use what are called relapsed memory models. They do things like write buffering, where a write instruction is just put in a queue to be done later. They do aggressive instruction reordering. The CPU might see a read and a write and decide to execute them out of order if it thinks incorrectly from our lock's point of view, that they don't depend on each other.
And if the CPU reorders your instructions, the entire proof of the Peterson lock just collapses.
It's gone instantly. In Peterson's lock, the sequence is vital. Set your flag, then set the victim, then check the wait condition.
But a modern CPU might reorder those writes.
It might. And if another thread observes that you've set the victim variable before it has observed that you've set your flag, the whole logic is broken. The synchronization guarantee is lost.
So a thread that should have waited doesn't. It thinks the coast is clear, and it enters the critical section at the same time as the other thread. Mutual exclusion is violated.
That's the danger. To fix this on a modern machine, you have to explicitly insert special instructions called memory barriers, or fences.
And what do those do?
They're like checkpoints. They force the CPU to complete all the read and write operations that came before the barrier, before it's allowed to issue any operations that come after it. It artificially restores sequential consistency, but only where you tell them to.
And here's the painful part. Memory barriers are slow.
Very expensive. They often require flushing CPU pipelines, waiting for caches to sync up across all the cores. The cost of inserting a memory barrier to fix a software lock like Peterson's can easily be more than the cost of just using a hardware-backed instruction.
And that cost equation is why we made the transition.
It's everything. Instead of writing these clever software logs and then manually injecting expensive fences, developers now default to hardware primitives called read modify write, or RMW operations.
Like test and set or compare and set.
Exactly. These are operations that the hardware itself guarantees are atomic.
Yeah.
And crucially, they have the necessary memory barriers built right into the instruction. So they solve the atomicity and the memory ordering problem at the same time.
So the classic algorithms taught us how to solve mutual exclusion in principle, but modern architecture dictates what tools we have to use to solve it efficiently.
That's a perfect summary. Modern practice is dominated by highly optimized locks, like CLHQ locks or MCS locks, which are all built on these RMW primitives. They're designed specifically to handle high contention by minimizing the cross-core communication that these pure software locks generate. The theoretical foundation is still essential, but the implementation has to rely on hardware support.
So this whole deep dive has really shown that the mutual exclusion problem isn't just some practical coding issue. It's a profound theoretical challenge. It touches on time, logic, and the physical constraints of memory.
We started by establishing the necessary conditions for correctness: safety, which is mutual exclusion, and liveness, which is freedom from deadlock and, ideally, starvation.
And we saw the incredible elegance of Peterson's lock for 2 threads, and then the guaranteed fairness of Lamport's bakery algorithm.
But we also learned that elegance has a cost. Solving this problem requires memory that scales with the number of threads that omega bound, and things like unbounded labels create practical limitations.
And most importantly, we understood why these classic software-only locks aren't really used anymore. They just can't survive the aggressive optimizations of modern CPUs without inserting those very expensive memory barriers.
But these classical protocols are still the essential roadmap.
Hmm.
I mean, understanding how Peterson's proof works or why the bakery algorithm is fair, that is the only way a programmer can truly reason about the subtle dangers of synchronization.
The hidden starvations and deadlocks that might still be lurking even inside a highly optimized library function.
Exactly.
Okay, before we close, here's a final provocative thought for you to chew on, one that builds directly on this complexity of liveness. We established that solving mutual exclusion requires omega memory. Now, consider a more complex lock, like a tree lock, where threads have to acquire locks at each level as they climb the tree.
Okay.
If a thread that holds a lock somewhere in the middle of that tree can suddenly and unexpectedly delay, let's say it takes an arbitrary vacation for a long time, can you still guarantee starvation freedom for the entire system?
Or does one thread's localized arbitrary delay cascade upwards? Does it force not just its immediate competitors, but all the threads waiting higher up the tree to stall indefinitely? Does that kind of delay fundamentally change the problem, maybe forcing us back to the weaker guarantee of just deadlock freedom?
It just shows you that in concurrent systems, progress is an incredibly fragile promise. Until next time, keep digging deeper.